to organize this nice conference. So it's a lot of work, so thank you. Also, thank you for giving me the opportunity to talk about this work. So it's rather recent work. It's 2 papers this year, whose main contributor is Valentin Crépel. He's about to start his PhD with Nicolas Regnault and myself. Part of the numerical data has also been done by Nicolas Clausen. If I manage to, if time allows, I'll mention his work right at the end. So he's an intern with Nicolas. And it's also based on this earlier work, which was done with Valentin, Nicolas, Philippe Lecheminant, and Andrei Krenovic. So roughly speaking, the motivation is what? Okay, we've heard a lot about topological order. So say you take 2 different topological order phases and you bring them together. What do you expect to find at the interface? So it's actually been a lot of work, various articles on this problem. For instance, this work is one of the many by Grossfeld and Schouten. They say if you take a Moritz state and a non-abelian spin singlet state, you should find at the interface a very non-trivial edge mode, so a gapless theory, where the central charge is 7/10. That's the universality class of the critical Ising model. So there's some non-trivial edge reconstruction. But most of the approaches, or actually I think all the approaches about this are done at some effective theory level. So for instance, this is some kind of paste and glue approach. You suppose first that the topological phases are separated by the vacuum. They don't talk to each other. So topological phase 1 has its chiral modes, its usual edge modes, like its interface with the vacuum. The topological phase 2 has counter-propagating edge modes. And you bring them together and they start interacting, and there's some edge recombination, and something survives, and that's your interface. So that's a gapless part, if you want, in this RG sense. You have these 2 CFT coupled. Part of these get gapped, you forget about it, and what's this gapless? So infrared theory is again gapless. That's your interface massless modes. But all this is done at some effective theory levels. For instance, that approach, you just completely forget about the bulk. You just say, okay, I just have this edge, no bulk, it just lives in the vacuum. In principle, it's not possible, because that's a chiral CFT. There's some anomalies, but you forget about it. You couple the things, and here you are. So what I wanted to do is actually try to make this controlled. And how do you make this controlled? You actually have to take the bulk into account. So we want to write a model state, like the Laughlin in that sense is a model state, that will describe everything. Bulk of topological order 1, bulk of the phase number 2, and the interface. And so the idea is with this to see if we can indeed see this kind of interface. Does it emerge? Do we have the right phenomenology? And also what happens at the microscopic level? Like what's the size of the interface, for instance? So that's a big motivation. So the outline of the talk will be as follows. First, I'll recall some basic facts about fractional quantum Hall model wave functions. In practice, mostly we'll be talking about the Laughlin state. Then I will move on to the matrix product state description of these model wave functions. That's going to be the elementary brick. When we have this, it's going to be actually very easy to build this model wave function describing an interface. So I will introduce this interface wave function, and from this, then we're going to see what we can say about these interfaces. So I'll start with a bit of quantum Hall. I mean, we've heard this many times, actually, this week and last week already. So before doing the fractional quantum Hall effect, you have to solve the one-body problem, 1 electron in a magnetic field. So 1 electron, or actually we're going to do bosons in a minute. So 1 particle charge coupled to a magnetic field and confined to 2 dimensions. So you pick your favorite gauge, you write your Hamiltonian. Here it is on the plane. And okay, maybe without entering too much into the detail, maybe 2 important features is there are 2 scales in this problem. One is an energy scale, it's a cyclotron frequency, it's purely classical. That's going to be the energy scale of that problem for 1 electron. And then the length scale, this one is quantum, there's some h bar in it. It's the length scale called the magnetic length. So in the semi-classical limit, you basically it's sending the magnetic length to 0. And once you remove these two quantities, everything is dimensionless. You introduce complex coordinates, you write this combination, and here's your Hamiltonian. Haha, you recognize a harmonic oscillator, so you know the spectrum. It's h bar omega c times n plus 1/2. So discrete spectrum. The one difference with harmonic oscillator that it's infinitely the channel, infinitely on the plane. if you have a finite sample, basically the degeneracy is the number of flux quanta you have piercing through your surface. And from now on, mostly we're going to concentrate on the branch of the this is not zero energy, it's 1/2 h bar omega c, so the lowest Landau level, we can just focus on this. And we're going to be working mostly on the cylinder. So when I'll talk about the matrix product state, it's going to be rather clear why the cylinder is a good geometry to do this. I mean, that's geometry that's adapted to matrix product state description. So on the cylinder, so basically we identify y and y plus l. So x is a non-compact direction, y lives on the circle, and that circle has perimeter L. So big L in the all of the talk would be the size of the cylinder, the thickness. And okay, you can again solve the Landau problem on this. It's not that much different. There's maybe a better gauge choice than what we did before is this. Why is this better? Because that does not depend on y. That means you have translation, an easy translation in the y direction. You don't have to worry about magnetic translation. It's a usual translation. And you can look at what are the lowest Landau level wave functions that are eigenstate of translation in the y direction. And you find this. So what this wave function is, actually, there's really two pieces. One, it's plane wave in the y direction, and it says the Gaussian localization in the x direction. And actually, so ky is a momentum. It's quantized because you have finite. It's a compact dimension. And what you find is x is basically locked by ky. So if you know the momentum in the y direction, you know the position up to a magnetic lens. Why is that so? That's because once you project to the lowest Landau level, x and y they no longer commute. They commute to ILD squared. That means y is the canonical conjugate of x. So if you phrase differently, py and x, it's the same thing once you project to the lowest Landau level. So that actually looks very interesting, because once you project to the lowest Landau level, you have some kind of phase space reduction. You start with 2 positions, 2 momenta. Once you project, you say, oh, wow, I only have 2, or 1 position, 1 momentum, or 2 positions, it's the same thing. So basically, you can label your state by just 1 integer. So it looks like it's 1-dimensional. So it's kind of 1-dimensional, but there is one thing to keep in mind, is that each orbital has a thickness of 1 magnetic length, while the distance between 2 orbitals, well, is controlled by the size of the cylinder. And so it's 2 pi over L times LB squared. So if the cylinder is large, and it should be large because, well, we want to do 2D physics, not 1D physics, so the typical correlation length of fractional quantum Hall effect is a few multiple of the magnetic length. So you need this quantity to be much smaller than this. That means all these orbitals, they overlap a lot. So it is kind of 1D, but there's huge overlap. So even if you start with a physical short-range interaction, once you write it in this picture, it's going to be super long-range. So it's not that easy to solve numerically. But still, that's going to be, when we're going to write matrix product state, it's going to be, and you might ask, it's a 2D problem. Why am I using matrix product state and not tensor network? That's why. Well, it's kind of 1D-ish. So, okay, so that was for the one-body problem. Now we're going to worry about the fractional quantum Hall effect. So you take your lowest Landau level and you fill it partially. So looks gapless, but then you add interactions. So how much you fill your lowest Landau level is controlled by the filling fraction. It's number of electrons divided by the number of states in the lowest Landau level. And typically, the wave function for n electrons or n boson is going to look like this. So there's a Gaussian factor. That's okay. That's on the plane. On the cylinder, that would be a slightly different Gaussian factor times some polynomial. That's analytic in the Z's. Symmetric for bosons, anti-symmetric for fermions. Or if you don't like first quantization, you can write it in occupation basis. So either you write this function or you have the list of all these coefficients, but that's how you write the wave function. The issue is how do you get which are the good states, and that's very, I mean, there's no exact solution. So either you do numerics like exact diagonalization, DMRG, or you cook up model wave function. That means you try to write down wave function that look good. That sounds pretty weird in physics, and why would you do that? Turned out for the fractional quantum Hall effect, this has a long history, and it works pretty well, starting with the Laughlin wave function. I guess you've all heard about, even people not working the fractional quantum Hall effect. And Laughlin guessed that, well, that's a good looking polynomial. And actually, So this is not the exact ground state of Coulomb interaction. Obviously, it's too simple. But actually, it is the exact zero energy state of some idealized interaction, which you can think of, it's a short part of Coulomb. So it's an ultra-local interaction. It's basically the derivative of the delta function. So once projected to the lowest Landau level, let's tell you that the wave function is the zero energy state as long as it vanishes with a power 3 when you bring two particles together. So that's a ground state. But turns out it's very good in the sense if you do exact diagonalization on your computer with Coulomb, you're going to find a very high overlap. So in the field, everybody believes that this describes the nu equals 1/3, and there's no question about this. For instance, this predicts that you should find collective excitation of charge E/3, where E is a charge of the electron, so there's a fractionalization of the charge, and this has been observed in short noise experiment. Something that hasn't been observed is that, well, there's a prediction that these charges, it's called anyons, they should have non-trivial braiding when you swap them, pick up phases, not just signs. This is harder to observe. There's some proposals with interferometry, but it's not, I think, as far as I know, not extremely conclusive. Another theoretical prediction is if you start to do the quantum Hall effect on a non-trivial surface, like a torus or something with G holes, there should be 3 to the G ground states. So one way to get some intuition about the Laughlin state is through the so-called thin cylinder limit. So I told you when you're on the cylinder should be fat, or you're not in the right regime. But turns out if you actually make it very thin, there's no physical reason why things should be held correctly, but they kind of do. So what happens if you make your cylinder very thin, then the orbitals, they don't overlap anymore. They're well separated. And if you now look at the Hamiltonian in that limit, it becomes something very simple called Haldane's exclusion statistics. It's basically, you will have a zero energy state as long as in 3 consecutive orbitals, there's at most 1 fermion. So, well, actually, you can write 3 ground states pretty easily. It's 1 fermion, nothing, nothing, 1 fermion, nothing, nothing. And these are translated by 1 or 2 units. That's 3 ground states you find on the torus, for instance.
So,
yeah.
So what's the range of Laughlin's Hamiltonian here in this basis? So in general, you said it's local interactions become long range.
Yes, the long range when
so
these overlap a lot. Well, I
they
guess
don't, so
here it's 3.
Okay.
I think. Oh, this doesn't make sense. There must be 3. I guess it's just a projector. You take 3 orbitals, and it's cost energy if there's more than 1 electron. I think. Actually, never checked that. I can see any possible answer. Okay, so that's this thin cylinder limit. And you can also use this picture to understand what happens at the edge. So what do I mean by an edge? So say you work on the plane, you put so many electrons, this is gonna, if you put finite amount of these, this is gonna actually make a droplet that is the shape of a disk. And then you multiply by any symmetric polynomial. This is still a zero energy ground state because as you bring a zi close to zj, it still vanishes with power 3. You haven't changed that. So it's still a zero energy. The difference is as you increase the degree of this polynomial, you start to increase a little bit the size of your droplet. And actually this is basically creating an edge excitation. So that's the kind of exact way to look about this. And you can count this polynomial. Every time you increase the degree of this polynomial, you're actually increasing the momentum. So that's angular momentum on the plane. But if you map this to the cylinder, it's really the momentum we were talking about. There's momentum along the compact direction. But there's a much simpler way to look at this is with this exclusion principle. So, well, you have to put a confining potential now if you really want to talk about dynamics at the edge. So the flat band that was the lowest Landau level now is not flat anymore. You've added some potential. And so, for instance, here is the ground state. So on the left of this is a quantum Hall liquid, and on the right is the vacuum. So on the left you have 1 particle, nothing, nothing, 1 particle, nothing, nothing. That's a ground state. Say it's going to be our reference for momentum. That's momentum 0. Say I want to increase the momentum by 1. What can I do? Well, I could say, well, maybe I'll try to move this guy outwards here. But actually, that will violate my exclusion principle, so that's not allowed. That means the whole bulk is frozen. I cannot move anything in the bulk. But on the edge, I can. I can take this guy and move it here. That's fine. And then I've created a new state that has momentum. Well, I've increased by 1 quantum of momentum. That means by 2 pi over L on my cylinder. So there's one state at energy 0. In the right unit is one state at energy 1. But the right unit is 2 pi over L. And then what can I do with momentum 2? Well, I can push these guys further up, or I can move this guy here. There's 2 states. And you can keep counting. And you will find actually the same counting as the number of homogeneous polynomials. And that's, again, that's counting partition of some integers. That gives you some cartoon picture. So this is also the spectrum of a chiral boson. And another game you can play, I haven't explained here, but you can also remove or add particle and see how much energy it costs. And then you'll see the charge aspect of this. You'll find that actually it's a compact boson with a certain radius. Okay. Right. And it's chiral because, well, you see the dispersion relation always go one way. So that was for Laughlin state, and there's a generalization of this construction that was Moore and Reed came up, I think in 1992. And they said, well, one way to construct model wave function is to take a conformal field theory, pick some operator called V of z, and write a correlation function like this. Technically, it's a conformal block. There's only the chiral part of the CFT. And this little thing here is it's a bit of a technical detail. It will come back a bit later, so I'll mention it. It's a background charge because, well, each electron, every time you add it, it adds some electric charge. At some point, you have to subtract it. Basically, why it's sitting here. And Moore and Reed said basically they came up with some kind of bulk edge correspondence, saying, well, our quantum Hall droplet, it has a gapless edge that's described as some chiral CFT. Well, take that chiral CFT, the same one, to describe the bulk in this way. It's kind of a recipe. For instance, the Laughlin state, actually, you can write it like this exactly. So for the CFT, you take, well, this compact chiral boson at radius square root of 3 that we just talked about. In there, there's a vertex operator, which is e exponential of I square root 3 phi, so you have to take m equals 3 to make the Laughlin 1/3. And if you compute this conformal block, you find exactly that Laughlin thing. That's exact. So you can rewrite Laughlin in this language. And there's other states you can write like this, like the Moore state, the Pfaffin state, which is supposed to describe the nu equals 5/2, and then some Xi states. Halperin state, that's an abelian state with 2 components, so that's if you add spin to the picture, which will come back in a second, because actually we're going to end up looking at an interface between Laughlin and Halperin. So Laughlin is 1 boson, Halperin 2 bosons. That's the thing to keep in mind. Okay. So matrix product states now. So something I haven't mentioned yet is entanglement. So before moving on to the matrix product state, I'm going to do brief, very short review of entanglement entropy for the topological order. So what's entanglement entropy? Where you take your system, so here we're going to have our quantum Hall droplet on the cylinder, you chop it in 2, part A, part B, you trace over B, you end up with a reduced density matrix of part A, and you compute its entanglement entropy. And for gap phases, you're supposed to have an real. That means the entropy of part A, it doesn't scale with the volume of A, it scales with the volume of the boundary of A. So in our case, that's going to be the size of the cylinder, L. So there's a part that's linear in L, that's for any gap phases. In fact, even most gapless phases, except I guess in some counterexample like free fermions. But anyway, gap phases are supposed to obey a real. What's interesting about topological order is there's a constant correction to it, which is universal. So the prefactor here is not universal. It depends on your microscopic detail. But this is universal. And for instance, for the Laughlin state, this is supposed to be log square root 3. And you can check it numerically. You put your Laughlin on the cylinder using some matrix product states we're going to present in a second. You plot the density of part A as you, so this is the size of the cylinder in unit of the magnetic length. So see, starting from 10 magnetic lengths to 30. You plot the entropy, you do a linear fit, and you extract this. You get typically 1% precision. Works pretty well. That was done before, so on other geometry without matrix product state, but here you get a much nicer precision. Okay, that's the entanglement entropy. Actually, you can go further and say, okay, maybe the entropy is not enough information. Might as well look at the whole spectrum of rho A, because that was the Leon idea in 2008. So you take your reduced density matrix. It has some eigenvalues. You write an exponential of minus, and you call this the entanglement energy. That's very much related to the coefficient, the singular value that you find in the Schmidt decomposition. It's basically the same thing. And you can plot this spectrum versus all the good quantum numbers you have in your system. So for the fractional quantum Hall effect, if you do this kind of cut, there's two good quantum numbers. It's the number of particles in part A and the momentum of part A. So here it's an example on this Laughlin on the cylinder. So versus the momentum ky, and for a given number of particles, that's fixed. And you see some things that looks like a chiral dispersion relation. Actually, it looks very much like the plot we saw in Steve Simon's talk last week, except he was plotting a real energy spectrum of the edge. And there was the same kind of spread that was interpreted as some irrelevant perturbation at the edge. So the conjecture here is basically this capture the edge physics, but in the bulk. So it's some kind of, again, bulk edge correspondence.
No. What determines the Schmidt rank of your decomposition?
Sorry?
What determines the Schmidt rank?
What determines the Schmidt rank? Typically, it's infinite. If you are on the cylinder with infinitely many particles, it's infinite. If you have finitely many particles, then it truncates somewhere. Then how much is the rank? Well, there's some conjecture that the rank is actually exactly how many states you can write in finite size with the sizes you've chosen. So you say you start with n particles, it takes some size. But then you look at part A, it has much fewer particles.
Yeah.
So say there's 6 particles in part A, then you took a big system. And how many states can I write down with 6 particles in there? Typically, that will be your Schmidt rank. And maybe another fun fact is if you start counting here how many states you have, you're going to find 1, 1, 2, 3, 5. Again, that same pattern. So it really reproduces. It's very much like the edge.
Still, for model wave functions, the rank is much smaller than what you expect for a general state.
Yeah. Actually, if you would take the exact ground state of Coulomb, you would find the same thing, plus a lot of garbage on top, which is kind of irrelevant in the DMRG sense because it's very low entanglement. So you can basically, this is an ideal state when you remove that jump. Okay, so matrix product state, what are they? So it's a way to encode many body states. So before I write a many body state, you can write as the sum over occupation numbers. In here, there are just some coefficient. So that coefficient, you just insist on writing as a product of matrices, some particular matrix element. So what kind of for instance, for the Laughlin electrons, M1 would be the occupation number of orbital 1, so that would be 0 or 1. M2 is 0 or 1, etc. So you have two matrices. You have A0 and A1. And there's some matrices where are some size chi by chi, we apparently don't know the size. Alpha L and alpha R just encode the boundary conditions if you have an open system. If you have a closed system, typically you trace instead of putting this. So first statement is any state you can write like this. Well, which is not very hard to convince yourself. Say you have some Hilbert space that's, I don't know, 100 million dimension. Well, you take A to be 100 million square, and you have enough freedom with all your coefficients to write any possible state. But that's basically useless because if you have to work with huge matrices, you haven't gained anything. So the much stronger statement is that most interesting state, like ground states or low energy state, you can write like this with a small chi. I'll try to convince you in a second why you can do that. So maybe let me say a bit more about these matrices. So there's two kinds of indices. There's this M, which is called the physical index. So I just gave an example for fermions, it's 0, 1. That's the occupation of some orbital. For bosons, it's any positive integers. If you're working with a spin chain with spin 1/2, it's up or down, etc. And alpha and beta, well, there are indices in this auxiliary space whose dimension is chi. And what do we know about chi? Well, actually, if you write the state like this and you do the Schmidt decomposition, you'll quickly see that chi a lower bound for chi is actually the Schmidt rank. So roughly speaking, chi is of the order of exponential of the entanglement spectrum, entanglement entropy. Sorry. So for the case of interest, our 2D gap phases, that means that chi will grow like it's going to be some exponential of L. That's a lot, but actually that's much better than a brute force thing that's exponential of the surface. That's just exponential of L. So that's a gain we have with matrix products. But that's also the limitation, is we cannot make L as big as we want. There's going to be a limit to how big the L we can do. But we can make the cylinder infinitely long at zero cost. That's why the cylinder is a good geometry to do this. Okay, so then the next interesting thing is if you take any of these Moore and Real wave functions that are written at some CFT correlator, this actually is exactly a matrix product state. So you don't even have to do a variational approach. You have analytically your matrices. So how does that work? Well, you take this, and actually to get the expansion in occupation basis, you just need to expand your V of Z in modes. Or in the cylinder, that's just a Fourier decomposition, if you prefer. And then you see that this coefficient, when you decompose this into occupation basis, is just something like this. So it's some various modes of V. Well, these modes, you can think of them as matrices. They're operators acting in the CFT. They're just infinite dimensional matrices. And it is an MPS with one little caveat, is that, well, each matrix depends on the orbital. So at orbital J, you have two matrices, B0, B1 for fermions, or B0, B1, B2, etc. for bosons, but they do depend explicitly on the orbital. So it is an MPS, but it's not translation invariant MPS. But turns out you can make it translation invariant because there's some relation that the matrix at side J, it's the same as a matrix at side 0 up to some gauge transform or some unitary transformation. So that means that this product you can rewrite like this, and now this is a translation invariant MPS. So that was first found out by Zaleter and Long in 2012, and found the correct U to use is this. And actually that's there's a way to understand this intuitively. Is what is this? So H here is a CFT Hamiltonian. So this first bit, if you want, it's a transfer matrix that propagates over 2 pi over L. That's the distance between two orbitals. And the little bit you have to add here is it's a background charge. It's that stuff you need to neutralize the charge of the electrons. So that's why you have to put. So you end up with these are the MPS matrices you should use. They're analytic. You know exactly what they are. And that will represent exactly your model wave function. There's just one little problem, is that they're infinite dimensional. So the computer will not be very happy about it. So that was the derivation for spinless fermion. If you want to do fermions with spins, which we're going to need in a second for the Harper-in state, you can rederive it. That's actually what Valentin did first. And you have similar looking formulas. So I was saying chi is infinite, so you need a truncation scheme. And in the conformal field theory, the natural cutoff is a conformal dimension. So you're going to, what we call Pmax, you're going to say, I'm going to remove all the conformal states that have some dimension higher than Pmax. And actually, when people do a numerical RG in CFT, it's called truncated CFT approach, they do the exact same cutoff. As long as the cylinder is not too big, that's a good approximation. And as you make your cylinder L bigger and bigger, you're going to need to increase your truncation. But in terms of quantum Hall, what does that mean, this truncation? That means, well, let's say that's your exact model wave function. This truncation is going to remove all the states that it's a truncation in momentum, basically. It's going to remove all the gray area. So it's not exactly like a Diamergy truncation. In Diamergy, you would just choose some chimax and truncate everything that's on top. But it's very similar. Why? Because this is kind of a linear spectrum, and actually the bigger the cylinder, the more linear it's supposed to be. So whether you truncate this or that, there's not much of a difference. It's okay. It's not the most efficient cut, maybe. The best cut would be to do a Diamergy type cut, but it's still not very far. And okay, so once you have done this truncation and you have the matrices, you can just put this in your computer. And you can do calculation about Laughlin or Murid. You can extract the topological entanglement entropy. You can do quasi-Hall braiding. You can do all kinds of things. So you can work on an infinite cylinder. Just you're going to have some limitation on how fat you can make that cylinder. But for Laughlin, typically you can do like 30 magnetic lengths. So it's still much bigger than anything exact diagonalization can do. OK, so now that we have the MPS building block, we can do the interface. So which interface are we going to look at? Well, we're going to put a Laughlin 1/2. So these are bosonic. It's a closed cousin on 1/3. It's just product of zi minus zj squared, not cubed. And we're going to make an interface with a Halperin 2-to-1 state. So Laughlin is 1/2. So we said this fractional excitation, the E/2. And at the edge, there's just one chiral boson. Halperin is actually a close cousin of Laughlin. It's the same interaction. The one difference is in here, the electron, they have spin up and spin down. So they have an internal degree of freedom, while in Laughlin, they're all polarized. So actually, we work with a convention that all the spins are down here. So there's 0 up spin, and all the density is in down spins. For Halperin, it's SU2 symmetric. So you have up spin and down spin. The density is 1/3, filling fraction. The elementary excitation here is E/3. I mean, they're quite different as far as topological order go. And this one has 2 chiral edge modes, one for charge, one for spin. So as far as interaction go, they're basically, so it's boson with just a hardcore interaction. It's just delta function. But since here you're allowed to have spin up and spin down, you have kind of a bit of a denser state than in the Laughlin case. And how do you actually can, if you want to do exact diagonalization on this, you can just take this Hamiltonian and add a chemical potential for the upspin and say, put that chemical potential 0 here, infinite here, and do exact diagonalization. Which at the end of the day, if time allows, I'll show you how our variational approach compares to exact diagonalization. Actually, Haldane had a prediction about what you should find at the interface, and basically you should find a single gapless mode with a free chiral boson at radius √6. Okay. We'll see if we find it. So what's a variational wave function? Well, it's actually very brute force. It's the simplest thing you could do. The most stupidest thing is I'm going to just glue my MPSs. Very simple. So now people doing MPS usually start screaming, I imagine, because I'm not allowed to do that because it's not the same auxiliary space. This contraction makes no sense. Here I have some auxiliary space A, here I have some auxiliary space B. How do I glue them? Well, actually, here there's something simple in the sense that the Hilbert space of Laughlin is a subspace of the one of Halperin. So in terms of CFC, it's a conformal embedding. That means I can glue them. That's easy. It's just one is a subspace of the other. So there will be some degrees of freedom here that basically don't talk to these matrices. So if you wish, the Hilbert space of B is a tensor product of 2 boson. And this is only 1 boson. So I connect one of the boson and the other run through. And that's the end. That's it. So maybe one comment is, so I was saying there's if you're working with an open system, so you will have the interface mode here, and you will have also edge modes on the left and right. The edge modes, they're controlled by what you put at the end of your MPS. So if you want to change the edge modes on the left, you will change what you put here. If you want to change the edge modes on the right, you'll change what you put here. But here, remember, now I have a much bigger auxiliary space that I need because I have 2 bosons. So if I change the Laughlin boson, I will indeed change the edge state here. What happens if I tweak the other boson? Laughlin doesn't care about it. So what actually, I'm going to change what happens at the interface. That means actually this is not one wave function. It's a family of wave function when I can put any state I want at the interface. Because at the interface, it's not just one state. I'm supposed to have a gapless series, so it's a whole family of states.
I thought you had a smaller auxiliary space for Laughlin.
Yeah.
Okay.
So, but basically, I put everywhere as a big, and I use only part of it. Yeah. So, well, then once you have this wave function, you can start to have a look if does it behave well. First thing you can plot is a density. So that's the x direction, because everything is translation invariant in the y direction.
So, but do you actually have some variational parameters?
Nope.
Because your slide was.
Yeah, it's called variational. Yeah, it's like Laughlin is called variational, but yeah, I should say it's a model wave function. Well, the parameter, if you want, is you can tweak the mode at the interface.
That doesn't change.
Okay, so that's a density. So x equals 0 is an interface. On the left, it's a Halperin state, and on the right is a Laughlin state, and it's spin resolved density. So orange is a density of spins up, which is, as it should be, 0 for Laughlin, 1/3 for Halperin, and the other one is spin up, so it interpolates between 1/3 and 1/2. So and this has 3 different perimeters, so by increasing perimeter. So the density looks well in the sense that if you're far away from the interface on the left, you have the right Halperin density. If you're far away on the right, you have the right Laughlin density, and things interpolate smoothly in the middle. Here there's some kind of little wiggles, but actually it's a finite size effect, because if you increase the size, they go away. So as far as density goes, this looks good. And also, this you might say, okay, the width of the interface is kind of 5 magnetic lengths, roughly. Okay, so that looks like a decent wave function. So now let's try to actually, we can look at the entanglement entropy. So entanglement entropy, we said, is a linear part minus gamma. Gamma, that depends on the topological order. In particular, gamma is different for Halperin, where it's supposed to be minus log square root 3, and for Laughlin is supposed to be minus log square root of 2. So what you can do is on your cylinder you cut, but you can cut in the Laughlin area. So if you do a cut, so that's x. So if x is like 17, very far from the interface, that's a gamma you extract. That's a good Laughlin gamma. If you do it for Halperin, this is a gamma you extract. There's a bit more finite size effects here, because Halperin is a bit more involved numerically, but roughly it works. It's reasonably precise. And in between, if you do the cut in between, well, it kind of interpolates in between. So that's gamma as a function of x, if you want, x being where you cut. So up to small oscillations, and basically the interpretation is that the finite size effect here is more sensitive to finite size. So sorry, the subleading terms to the entropies are more sensitive to finite size than the leading terms. This gives you a smooth transition between the 2 bulk topological entanglement entropies. And there's no particular sign of the gapless mode, in the sense that at the interface, you still have an area law. You might expect, oh, it's a 1D critical thing. I might expect the Cardi formula. Well, not if you do that cut. But well, there's a way to actually get the Cardi formula, is to do a cut like this. So it's some kind of leaving when cut. So instead of doing cut that preserve the angular momentum, so imagine the interface is sitting here, and this part here is going to start to probe the interface. So the idea being that if you have a 1D system, so that's a 1D system, and this is part A, and it has size L, and the total size is big L. By varying small L, you can extract the central charge. So, but now we're in 2D, so we have to do this kind of cut, and the idea will be to make this vary and see how the entropy changes. And well, if things works well, you should find that's the Cardi-Calabrese formula. So you have to be a bit careful about this. I mean, we have a bit more parameters than just L here. For instance, there's a width here you have to pick. And basically, you want to pick that not too small that you have the interface. Not too big because, I mean, in that direction, you expect area low. So if this is too big, there's going to be lots of entanglement here. And because we work with a finite bond dimension, we're going to have saturation effects. So there's basically a window in W where this works well. And the dependence in W, we're not interested, so we're just going to do this subtraction to just have the L dependence. And here's the plot. So in black is a theoretical, that's a Cardy-Calabrese formula. This is little l over big L. And you see that there's a whole region here in which it works well. So as long as L is not too big, nor is it too small, things work well. But you have the same thing in 1D. If you take your favorite spin chain, critical spin chain, and you do entanglement entropy, it's not going to work here. It's going to work in the middle. I mean, here's this obvious finite size effect. If you here, that means your region A is tiny, like there's 2 spins, too small to be in the thermodynamic limit. If you here is region B, that's too small, same problem. So it works well if you're in the middle. That's expected, yeah?
How are you supposed to make that cut? Because at the end of the matrix product state, if people try to do some singular value decomposition, it seems like it cuts the whole cylinder at the same
You have to, because you have to decompose. You have to go back to the orbital and decompose the orbital into support in here or support in here.
okay.
Yeah. You have to modify there's a way to do it, but you have to remember you're actually not 1D, you're 2D, and you know how to modify things. It's not a cut just in auxiliary space now. Like the other one before were, then that's an easy kind of entanglement entropy to get. This you have to work a little bit more. So it works pretty well, and so you have 3 system sizes. So blue is 10 magnetic lengths up to 12. And you also see that even where it doesn't work, as you increase the system size, it does seem to converge to the right thing. So in the middle is just a derivative of this to see a bit more what happens in the middle. And basically, you can just make your computer do a fit with a Cardy-Calabrese formula to extract the central charge. And you find with 1% precision, basically, C equal 1, what you expect for a chiral boson. So things work actually surprisingly well, even though that was a very crude model wave function. So this tells us that indeed there seems to be a C equals 1 CFT at the interface. And it's chiral because we use C over 6. C over 3 would be the full boson. C over 6 as for a chiral CFT. So it's just a factor 2 here because within this scheme it's counted twice. That's where the 2 is coming from. Okay. And you can check that indeed things are very different whether you do this in the bulk or at the interface. So on the interface, indeed it works well. If you go deep in the bulk of the Halperin or the Laughlin, you're very far from the critical thing. So it is really an interface effect. So the next thing one might want to extract is the compactification radius. I mean, compact boson, they all have the same central charge 1, but so how can you extract the compactification radius? One first idea would be, well, what I should do, I know in 1D I know how to do it, I should just do a 2-interval entanglement entropy. That will give me the radius of compactification. Turns out here our systems are not big enough. We can't do it. So another way to do it is actually, well, the compactification radius in that setup, it tells you what is the charge of the elementary excitation you can have. Basically, radius square root of 6, which is what we expect, means we should be able to find an excitation of charge E over 6 sitting at the interface. And how to do it? Well, that's what I was saying. We have this Hilbert space that's much bigger on that side of Laughlin. We can tweak it. So by tweaking that knob, we change what happens at the interface. So we can just change the charge and see how much charge there is at the interface. So in green, it's the density, so the spatial resolved density of the ground state at the interface, and in red of the first excited state. And you can just measure how much charge excess you have, and you find E over 6. So basically, we've done this for by increasing the charge by increment. You look at the slope, and you find E over 1 over 6 for the charge and 1/2 for the spin. And that gives you what you want, basically. That's the compact boson of radius square root of 6. Okay, so basically we have the right phenomenology. We have what we expect for the central charge. We have what we expect for the compactification radius, but then you might worry about microscopic, about energetics. So what you can do is compare with an exact diagonalization with this Hamiltonian I was showing you before. So you have the hardcore interaction for the bosons, and you do an infinite ramp in the chemical potential for the upspin. So on the left, the Halperin side, no chemical potential. On the right, infinite chemical potential. Of course, now you're limited with how many particles you can put. So we put 4 upspins, 9 downspins. We take 21 orbitals. So that's 200 million size dimension Hilbert space. You do, and you compute, you do length, you do compute the first few eigenstates. And here's the spectrum. Sorry, no. Here we just do the ground state. We do the ground state, and we do overlap with our variational wave function, and that's huge. So it works very well. Then you might worry about the first excited state. So you can. So this is a bit. It's less particles. This is only 15 orbitals. I didn't write how many particles. Okay, here is the energy spectrum. So this is a bit messy because, well, there's kind of 3 phenomena mixed in together. There's the interface capless mode. There's the edge modes, because now we have a finite size system, so we also have edges on the left and the right. And then this is the bulk energy here. So in that lower energy part, it's a bit complicated because there's edge modes on the left, edge modes on the right, and interface modes in the middle. So you kind of have to guess which are which by doing overlaps with your MPSs. And so the one where we have written the figures are the one that we can reproduce with the MPS. And you see the overlaps, they range, like the worst one is 96. I don't know if we can really see. It's a bit too small. But the overlaps are pretty good, not just for the ground state, but also for the first few small energy states. At least the ones that are at the interface, because some of these are at the edges. And if you want to get rid of this bulk effect and these edge effects, one way to do it is to project this interaction within the manifold of matrix product states. Forget about the rest. And then to look what's the energy cost of this guy. So that's the part that Nicola Clausen did with a matrix product operator. So now you forget about, you just take all the possible MPSs, because you can change what's happened at the interface, so you have many of them, and you look at this this microscopic Hamiltonian, you look what is you diagonalize this basically in this subspace. And that gives you an idea about the dispersion relation of that law. And you see actually it's there's lots of spread. The Fermi velocity is pretty high. That's why here you very quickly you end up in the bulk. And we think that is due to the fact that the Hamiltonian is very brutal. We've put infinite chemical potential all of a sudden for the upspin. So it's not a smooth transition. Okay, so that was for boson. You can do the same thing for fermions. Numerically, it's a bit more expensive. It turns out for this MPS, as you decrease the filling fraction, it costs a little bit more. You can still do it. It just will not converge as quickly, so it costs more. But you find the C equals 1, because it's still supposed to find a compact boson. The one thing is different is it's a different compactification radius. Here is square root 15. But you find it. And that's it. A bit early. So in conclusion, so I presented you a variational Ansatz to describe the interface between the Halperin and the Laughlin liquids for fermions or bosons. What's interesting is you can extract the phenomenology, like central charge and the compactification radius, or the charge of elementary excitation, but you can also look at the macroscopics. And this, in principle, should be we should be able to extend this to any kind of tensor network, like PEPS approach. The one thing that's non-trivial in general is how to glue the two auxiliary spaces. Here, the trick, what made things simple, is that one Hilbert space was a subspace of the other one, but that's not very generic. So how does one do the generic case? Well, there's one way to do it, is this, the auxiliary space really, it's the same Hilbert space as the CFT Hilbert space that describes the hedge modes. So think of it as being the hedge modes of the Halperin, or some, anyway, of state A. This is the edge mode of state B. What can you do? Well, you can couple them. Basically, it's, again, this space and glue approach. You have one Chiral CFT, one anti-Chiral. You couple them with your hollow hoppings between electrons. And then you do RG numerically with truncated CFT, and you keep everything that's gapless. And anything that's gapless, you can use it to glue these guys. So in principle, you might be able to glue different MPSs in the generic case, but there's a cost. You have to do this numerical RG. And that's it. Thank you very much.
When you did your ED, then you had a problem that you had the two edge states. Is it possible to deform somehow your edges so that they become gapped? What I mean, for example, if you take S equal 1 chain, then the edge will be edge spin, and one spin 1 half, it will gap out. That edge both and only the other will remain.
Now here I don't know how to do that here. I'm going to go with, I've never heard anyone talking about this, so it's not doable, but yeah, I would not know how to do it.
So suppose you have just one quantum phase with boundary, and you can use MPS to represent the bulk, and you have an edge. So with the dangling bond of this MPS, and I suppose that corresponds to some compactive theory.
Yeah. Yeah.
Now you consider boundary between two different regions, junction between two kinds of MPS. And you mentioned that there's a mismatch between the dimension of the virtual space. So you only couple part of the Hilbert space on one side to the other side. So you have some partially dangling bond or something.
Yeah. Yes.
I suppose corresponds to the remaining edge components.
Yeah, it corresponds to what's at the interface. Yeah.
So my question is, so without doing any calculation, once you introduce this kind of partial matching, you already know what kind of properties.
In that easy case, yes. Yeah.
Sometimes you.
But usually it's not that simple because you don't have one that's included in the other. Because the physical picture is pretty simple here. Halperin, there's two bosons, one charge and one spin. The other is just one boson. The bosons that coincide, they gap out. And that's it. And the other one is left. So you're left with one boson. That's a very crude picture. But in general, it's not so easy. It's not easy to know what is going to gap out. Say you take Laughlin 1/2 and Laughlin 1/4. What does gap? That's not clear. I think nothing gaps. And you're left with the two.
You still know how to couple them when there's a mismatch in.
Well, we have this proposal, but we are working on implementing it, which amounts to really take the chiral modes of the one, the anti-chiral mode of the other, add the perturbation, which is electron hopping, and do the RG on the computer. So part of this is going to gap out. You forget about it, but you have still lots of gapless states. And each such gapless state, you can use it to glue. And if you want to describe the different interface modes, you have to put a different part of that massless spectrum.
So I still don't fully understand the structure of your MPS that describes quantum Hall process. So clearly it depends on size of the circumference of the cylinder.
So you mean before the interface, just for the bulk?
Yeah, right.
Yeah.
So in the limit of the cylinder, clearly it reduces the product space. So
Yes.
I think chi should go to 1.
Yeah.
So I think
But that's a part maybe I haven't explained, is how do you choose the truncation? I mean, I said you truncate, but basically for a given truncation, there's going to be a maximum L you will be able to reach. But if you do take this most brutal truncation possible, you just keep one state, like bond dimension 1, you will recover that thin cylinder limit.
Oh, yes.
You will get this 1, 0, 0, 1, 0, 0. But as you start to increase the size of your cylinder, you want the subleading terms, you need to have a Pmax that's large enough.
Do you have any guiding principle for choosing the optimal value of Pmax?
But yeah, the guiding principle is you know how much entanglement entropy
yes,
your state is supposed to have. Yeah, so the bond dimension should be exponential of entanglement entropy. So now the remaining factor is, as a function of Pmax, what's the bond dimension? It's also exponential. It's Cardy formula. So now you have to get the two to match. But yeah, that gives you a guiding principle for how big. But in practice, you just check numerically. Do things are things converge in Pmax or not?
You said if you had a longer chain, then you could use the 2-interval entanglement entropy to get the boson radius.
Mm.
So is there some Cardy-like formula involving the boson radius in that case for 2-interval?
Yeah, it's Vincent, Pasquier and Chirachi, and yeah, entropy with 2 intervals for the compact boson. That's formulas. Yeah, basically you end up with a partition function on some higher genus manifold. So if you take the second Rényi entropy with 2 interval, you have torus partition function that depends. We know how.
I'm wondering, so it's not trivial to do it, but non-abelian case.
Yeah, non-abelian case, you'd have to do this RG. I don't know any other. Abelian case, I guess you can do. It's a bit easier. Yeah.
I don't know how to practically implement that in MPS interface. How to do it. In principle, we can find some vector operator which don't have interface.
Yeah, so I guess this will give you an idea about what gaps, what doesn't.
Yeah.
So maybe you can take a shortcut this way. Yeah.